A mysterious pulse is emanating from the Earth's core, and scientists are scrambling to figure out what it could mean. Now, before you start imagining wild theories, hear me out. This isn't some far-fetched sci-fi scenario. We're talking about something real, something that has been quietly disrupting the natural rhythms of our planet in ways we don't fully understand yet. This pulse isn't like any seismic event we've experienced before. It's subtle, almost imperceptible, but its impact is undeniable. Imagine if the heart of the Earth itself was beating in a strange, irregular pattern, sending vibrations throughout the entire planet, almost as if the Earth was trying to communicate with us. What if this pulse isn't a random anomaly? What if it's a sign of something much bigger, something we're just starting to uncover? Could it be a new phase in the Earth's internal processes? Could it be a harbinger of a greater, more catastrophic event on the horizon? Or is it simply a coincidence that we're only now noticing? The Earth's core has long been a mystery, hidden beneath miles of solid rock, but advancements in technology have allowed us to peer deeper into the planet than ever before. We've learned about the inner workings of the Earth's layers, but there are still so many things we don't know. Why are these pulses happening now? Why is there a sudden uptick in their frequency? And why does it seem like the Earth is sending these messages at all? What's even more baffling is that these pulses don't just show up on seismographs like you'd expect from regular earthquakes or volcanic activity. No, these pulses have a different signature, one that doesn't align with any known seismic event. It's almost as if the Earth itself is sending out these subtle vibrations, as though it's trying to tell us something important, something that could change everything we know about our planet. Now, the real question here is, what do these pulses mean for us? How will they affect our world, our environment, and even our daily lives? Could they be signaling a larger shift within the Earth's crust, or perhaps even a change within the core itself that could ripple outwards in ways we can't yet comprehend? And why are scientists only just beginning to take this seriously now, when the evidence has been there all along? It's not every day that we hear about something so strange and potentially groundbreaking happening beneath our feet. But now that this mysterious pulse has come to light, it's up to us to dig deeper and understand its true significance. Something's going on down there, and the question is, are we prepared to face whatever it might bring? Is the Earth really trying to warn us, or is this pulse just another piece in the ever-unfolding puzzle of our planet's complex behavior? In the next few moments, we're going to explore everything we know about this pulse, where it's coming from, what it might mean, and how it could impact the world we live in. So buckle up, because the mysteries of the Earth's core are only just beginning to unfold, and this pulse might be the key to unlocking some of the planet's deepest secrets. Stay with me, because what we're about to dive into is unlike anything you've ever heard before. And remember to subscribe to the channel for more major updates like this one. As the scientific world continues to reel from the discovery of the Earth's mysterious pulsing behavior, a singular explanation is beginning to emerge, one that dives deep below the planet's surface, far beyond what the human eye can observe or even fully comprehend. Among the countless theories proposed, ranging from tectonic anomalies to cosmic influences, one possibility stands out for its compelling blend of data-backed insight and planetary-scale impact: a sudden and significant acceleration in the movement of molten iron within Earth's outer core. While it might sound like a distant, abstract concept to the average person, this subterranean phenomenon could very well be the beating heart behind the rhythmic tremors now being picked up by sensitive instruments across the globe. It's a hidden current of energy, one that stirs beneath our feet with unimaginable force and complexity, and it may be speaking to us louder than ever before. To fully grasp why this explanation is so captivating, and potentially so consequential, we need to take a moment to understand the sheer scale and importance of the Earth's inner structure. Beneath the fragile crust we walk upon lies a churning, dynamic system of layered elements, each playing a role in the balance and behavior of our planet. The outer core, which begins nearly 3,000 kilometers beneath the surface, is a vast, fluid ocean of molten iron and nickel. Unlike the solid inner core, which sits like a hot, dense sphere at the planet's very center, the outer core is in a constant state of motion. Driven by heat from the inner core and influenced by the Earth's rotation, this molten metal flows in complex, ever-shifting patterns, patterns that are responsible for generating Earth's magnetic field through what's known as the geodynamo effect. But these flows are not static. They are not predictable like ocean currents or wind patterns. They are turbulent, chaotic, and under certain conditions, they can change rapidly and with dramatic consequences. Recent high-resolution data collected from satellites and deep Earth monitoring stations have revealed something extraordinary: localized surges in the speed and direction of these molten iron flows. These aren't minor shifts. In some areas, the flow appears to have accelerated significantly over the past few years, creating what researchers are calling jet streams of liquid metal thousands of kilometers beneath the surface. These subterranean jets are not like anything we've observed before. They cut through the outer core with startling velocity, creating pressure fronts that press against the solid inner core and distort the shape of the mantle above. And this, scientists believe, may be the root cause of the Earth's strange pulse, a subtle but powerful reverberation being transmitted from the core all the way to the crust, echoing outward like a slow, methodical drumbeat. But the implications go far beyond a rhythmic tremor. When molten iron begins to surge in this way, it doesn't just affect magnetic fields or cause minor pressure changes. It can alter the very fabric of geophysical stability. The Earth is a tightly balanced system, and even small changes deep underground can manifest in surprising and sometimes alarming ways at the surface. Imagine an invisible engine buried at the center of the planet, suddenly ramping up its revolutions per minute. The result isn't instantaneous chaos, but rather a slow buildup of strain, one that begins subtly and then grows, pressing against fault lines, shifting plates, and potentially even altering the frequency of seismic events over time. The pulsing, in this sense, could be an early warning sign, a precursor to more overt geological changes waiting to be triggered. What makes this theory especially compelling is how well it lines up with other, seemingly unrelated anomalies we've been observing in recent years. The Earth's magnetic field, for instance, has been behaving unusually, with the magnetic North Pole drifting at an unprecedented rate and localized areas of weakening field strength appearing in unexpected places. At first, these changes were considered part of a natural fluctuation, part of the field's long-term wandering behavior. But now, with mounting evidence of erratic iron flow deep beneath the surface, a new picture is beginning to form. It's not just the magnetic field that's changing, it's the source of that field itself. If the outer core is indeed moving more violently, with faster and more erratic flows of molten metal, then it stands to reason that the pulse we're detecting is just one piece of a much larger puzzle, one that involves magnetism, heat transfer, core mantle interactions, and perhaps even rotational dynamics. The consequences of such a change are difficult to overstate. If these molten iron surges continue, or worse, if they increase, they could lead to a cascade of effects that extend far beyond subtle tremors. Geodynamic models suggest that prolonged acceleration in outer core flows could shift convection patterns in the mantle, affecting volcanic activity, plate tectonics, and even the rate at which the inner core grows. In extreme cases, it could even prompt a geomagnetic reversal, where the north and south magnetic poles swap places, a process that has occurred many times in Earth's history, though not within recorded human civilization. The pulse, then, might not just be a curiosity or a blip on a seismograph. It could be a siren call, warning us of an awakening deep within the Earth's hidden engine room. And yet, the question remains, what has caused this sudden shift in molten iron flow? Why now, after centuries or even millennia of relative stability, is the outer core behaving differently? Could it be the result of heat variations from the inner core? Is it a reaction to changes in Earth's rotation or gravitational interactions with the Moon? Or is there an external force, perhaps even of cosmic origin, that's subtly nudging the planet's deepest systems into a new phase of motion? Scientists are racing to find answers, poring over terabytes of data, simulating core behavior with supercomputers, and drilling deep into the Earth's crust in hopes of capturing clearer readings. But for now, one thing is clear: the pulsing Earth is not silent. It is speaking. And the accelerating iron within its core may be the first whisper of something much larger approaching on the horizon. To better understand the potential consequences of this accelerated iron movement within the outer core, We must now turn our attention to the boundary where this turbulent sea of molten metal meets the bottom of the mantle, a transition zone known as the core mantle boundary, or CMB. This interface, while invisible and buried beneath nearly 2,000 miles of solid rock, is not merely a passive dividing line. It is a dynamic, reactive region where energy, heat, and momentum are exchanged in staggeringly complex ways. Think of it as a pressure valve or a fault line within the deep Earth itself, constantly balancing thermal gradients, responding to the ebb and flow of the outer core's convective currents. Now, with molten iron surging faster and with more directionality than previously recorded, the CMB is no longer operating under stable, predictable conditions. It is under new stress that is beginning to warp its thermal profile and may be initiating entirely new mantle behaviors previously unseen in modern geological time. What makes this even more intriguing is the notion that changes at the core mantle boundary don't simply stay confined to that depth. Instead, they ripple upward in slow, deliberate waves, gradually influencing the properties of the solid rock above. This isn't a fast or chaotic reaction, it's more like a subterranean tide, slowly rising beneath the rigid lithosphere. Thermal anomalies begin to form. Slight shifts in mantle viscosity take place. Over time, regions of the lower mantle that were once dormant may begin to exhibit new movement patterns, feeding into the upper mantle's convection cells that are, in turn, responsible for driving plate tectonics. In other words, the pulse we are detecting might not just be a rhythmic signal from below. It could be the physical manifestation of deep mantle readjustment, a slow awakening of geological forces that have been asleep for centuries, perhaps longer. And what does this mean for the Earth's surface? While we are not yet witnessing overt geological catastrophe, there are subtle patterns emerging, minor yet unusual upticks in regional seismicity, unexpected variations in geothermal output in isolated locations, and even the slight reactivation of fault lines once considered dormant. Scientists in Iceland, for example, have noted a curious increase in deep, low-frequency tremors originating not near volcanic systems but from beneath what were thought to be stable continental zones. Similarly, in areas like the Pacific Northwest and parts of Central Asia, researchers have picked up on faint but persistent harmonic vibrations, subtle, low-amplitude pulses that seem to have no clear tectonic trigger. And while no one is sounding alarm bells just yet, the data is beginning to form a picture, that of a planet being stirred from within, not by surface-level mechanics, but by the immense and ancient forces rising upward from the depths of the core itself. This brings us to a fascinating and somewhat unsettling concept: thermal coupling. As the outer core's flow becomes more erratic and energetic, it does more than just press against the base of the mantle. It transfers heat with greater intensity. This increased heat exchange doesn't just warm the rock above, it alters its physical state. Regions that were once solid and immobile may become more ductile, more pliable, and more susceptible to vertical motion. Over time, these areas could act like underground lava lamps, slowly rising plumes of heated rock, known as mantle upwellings, pushing upward toward the crust. These upwellings may take thousands of years to reach the surface, but their journey begins now. Their initiation, sparked by the changing behavior of the outer core, marks the quiet start of a long-term geological transformation. One that begins far below, and yet may shape the very continents we stand on. What's particularly compelling, and has geophysicists glued to their monitors, is how this increased heat flux is affecting localized gravitational anomalies. That's right, the pulsing behavior and inner core disturbances are, in some places, actually measurable through tiny fluctuations in Earth's gravitational field. Satellite missions such as GRACE and its successor GRACE-FO have detected minute but consistent changes in mass distribution across the globe, particularly near regions believed to sit atop mantle plumes or subduction zones. At first, these changes were attributed to water movement, glacial melt, or seasonal mass shifts. But as the data has piled up, patterns have emerged, patterns that don't align with surface processes but rather suggest an invisible hand from below. It's as if the Earth's deep interior is rearranging itself, and the planet's very mass is subtly shifting in response. This revelation of mass displacement due to core-induced mantle activity, adds a layer of complexity that few had considered. When mass shifts within the planet, even slightly, it can affect Earth's rotation, the distribution of tectonic stress, and even atmospheric circulation in the long term. It sounds like science fiction, but it's rooted in hard data. The Earth is not a perfectly rigid sphere, it is an interconnected, breathing system. A change in the flow of iron deep within the planet can, through a cascade of interactions, lead to a change in how the air moves above our heads. This is how profound the potential chain reaction can be. And while it may unfold over decades or centuries, the pulse we're observing now could be the tremor that sets it all in motion. Even now, as sensors record the steady rhythm of the Earth's new heartbeat, there is a sense among researchers that we are standing at the edge of a deeper understanding, one that stretches far beyond geology and into the realm of planetary evolution. What if we are not just witnessing a temporary shift, but a transition into a new phase of Earth's internal behavior? One that has happened before in prehistoric times, unnoticed and unrecorded, but which left its mark in the fossilized stress fractures of ancient rock? Could we be entering such a phase again, only this time with the tools to see it coming, and perhaps even the foresight to prepare? While the changes deep within the Earth's core are undeniably significant, there is another force, equally monumental in scale, yet unfolding in an entirely different realm, that is contributing to the unexpected rise of the ground. Unlike the molten iron currents buried thousands of miles beneath our feet, this phenomenon is much closer to the surface and, in many ways, more visible to the human eye. It begins in the polar regions, where towering glaciers and sprawling ice sheets, ancient giants that have held their place for millennia, are rapidly losing their mass. These icy structures, long considered immovable in the grand clockwork of Earth's geology, are now melting at an unprecedented rate. And while it's easy to focus on the loss of ice itself, the real story, the deeper geophysical consequence, lies in what happens after that ice is gone. You see, glaciers are more than just frozen water. They are, quite literally, immense weights pressing down on the Earth's crust. Over tens of thousands of years, these glaciers have pushed the lithosphere downward, deforming the Earth's surface like a slow but steady thumb pressing into a ball of clay. This process, known as glacial isostasy, has quietly shaped the topography of our planet. The crust beneath a massive ice sheet can sink by hundreds of meters, and the mantle beneath it responds by slowly flowing away from the area, displacing mass across the globe. But as global temperatures rise and these glaciers retreat at alarming rates, that pressure is lifted. And the Earth, ever dynamic, ever reactive, begins to push back. This rebound isn't a quick snap, like a spring uncoiling all at once. It's a creeping, subtle motion, occurring over years, decades, and centuries. Known as isostatic rebound or post-glacial rebound, it represents the Earth's attempt to re-establish equilibrium. The ground beneath the once glaciated region starts to rise, not just slightly, but in some areas, by centimeters per year. In geological terms, that's astonishingly fast. And this vertical motion doesn't just affect the areas where the glaciers once stood. As the mantle beneath these zones begins to flow back in, other regions, sometimes thousands of kilometers away, respond by shifting, adjusting, compensating. The planet is in a constant balancing act, and every change in mass, no matter how localized, sets off a chain reaction in the surrounding crust. Nowhere is this more evident than in parts of northern Canada, Scandinavia, and Alaska, places that were once buried beneath kilometers of ice during the last ice age. In these regions, scientists have measured uplift rates that are among the highest in the world. In some cases, the land is rising by more than a centimeter per year, a staggering rate when viewed on a geological timeline. But it's not just ancient glacial zones that are affected. The redistribution of mass caused by this vertical motion is also subtly warping coastlines, tilting lakebeds, and even affecting seismic stress along tectonic boundaries. Entire drainage patterns are being altered, with rivers shifting their courses as land slowly lifts beneath them. It is, in a sense, the Earth reshaping itself in response to a change that began not beneath the surface, but above it, in the sky, as temperatures climbed and ancient ice began to vanish. And while this rebound may seem like a slow-motion response, its effects are becoming more pronounced. Coastal communities are witnessing strange tidal anomalies, places where sea levels appear to be dropping, not rising. But this isn't because the ocean is shrinking. It's because the land is rising out of the sea. GPS sensors mounted on bedrock are confirming what locals have begun to notice anecdotally, that docks are getting higher, tide lines are shifting, and low-lying islands are ever so slightly gaining elevation. These are the real-world symptoms of isostatic rebound in action, and they suggest a planet in the midst of an ongoing vertical reshuffle. What was once perceived as stable is now subtly in motion. What makes this entire process even more fascinating is how it ties into the redistribution of mass on a planetary scale. When ice melts, the water doesn't just disappear, it flows into the oceans, increasing sea levels globally. This movement of mass from the poles to the equator doesn't go unnoticed by the Earth's crust or its internal structure. Gravity itself is altered, ever so slightly. The Earth's rotation, wobble, and even the shape of the geoid, the imaginary surface that represents sea level, begin to shift. These are subtle changes, yes, but they build upon one another. Over time, they can change stress loads on fault lines, cause microseismic activity, and further encourage the surface to readjust. In this way, the melting of glaciers does far more than threaten coastal cities. It sends a ripple through the very skeleton of the Earth. And this ripple is not something that can be easily reversed. Once the rebound begins, it continues on a momentum of its own, fueled by the immense elasticity of the Earth's crust and the slow viscosity of the mantle below. It's as if the planet, long held in place by Ice Age constraints, is now being unlocked. Freed from its frozen shackles, it begins to stretch, rise, and reposition itself. And because these changes are gradual, they go unnoticed on a day-to-day basis. But when viewed on the scale of decades or centuries, the shift becomes undeniable. Mountains are growing taller, valleys are deepening, and the bedrock beneath our feet is, quietly but persistently, on the move. As the land continues its gradual but unstoppable ascent, pushed upward by the invisible hand of isostatic rebound, we find ourselves standing in the midst of a geological process that is both ancient and ongoing. One that began long before the first human civilizations formed and will continue long after our modern cities have faded from memory. And yet, the true depth of this story is not just in the movement of bedrock, but in the far-reaching effects it has on everything resting atop that bedrock, from delicate ecosystems to the sprawling infrastructure of human society. What we often take for granted as fixed, from coastlines to continental divides, is subtly warping, shifting, and adapting in response to the ongoing release of the Earth's compressed crust. This rebounding land is not merely rising, it is reshaping the stage on which life unfolds. Take, for instance, the delicate balancing act between land and water in regions experiencing uplift. As these areas rise, watersheds are distorted, rivers that once flowed smoothly toward the ocean find themselves gradually redirected, their gradients subtly altered. This shift can cause unexpected flooding upstream or the drying out of wetlands that previously thrived in equilibrium. Lake basins begin to tilt, causing water to migrate slowly to one end, altering habitats and nutrient flows. Over the span of decades, entire freshwater systems can evolve into completely different ecosystems, all because the land beneath them is no longer where it once was. And while this change is glacially slow on a human time scale, the impacts on wildlife, agriculture, and even human planning are real and mounting. Moreover, the very idea of what constitutes a flood zone or coastal region begins to blur as isostatic rebound subtly lifts some areas while the sea encroaches on others. In places like southern Finland or parts of Hudson Bay, land is rising so rapidly that new islands are literally emerging from the sea. What was once seabed is now beach, and what was a coastline a generation ago may today be inland. For city planners, this is both a gift and a curse. On one hand, land rising out of the sea may appear to be a natural defense against sea level rise. But on the other hand, this vertical motion introduces a host of geotechnical complications. Foundations designed decades ago are suddenly under different pressure loads. Piers and ports built to a particular sea level must be re-evaluated. Drainage systems, sewers, and flood defenses no longer align with the topography they were built for. In this way, the Earth's silent vertical shift becomes an engineering puzzle with real-world stakes. Even beneath our feet, the implications continue to unfurl. Underground utility lines, those vast, unseen networks of pipes, cables, and conduits that supply our cities with water, electricity, and communication, were laid out with a certain static assumption of elevation and stress. But as the ground beneath them slowly rises and adjusts, subtle strain is introduced into the system. Joints that were once properly aligned begin to stretch or compress. Foundations laid deep into bedrock may encounter unexpected torsion or vertical displacement. Over time, this can lead to microfractures, leaks, and service disruptions that seem inexplicable, until one considers that the very ground these systems were embedded in is on the move. The planet is telling its story through these tiny clues, and those paying close attention are beginning to piece the narrative together. Another consequence of isostatic rebound, and perhaps one of the most overlooked, lies in the redistribution of gravitational potential energy. As land lifts and mass is moved vertically, the gravitational field in the area subtly changes. This may sound theoretical, but the effects are measurable. Satellite missions such as GRACE, Gravity Recovery and Climate Experiment, have documented shifts in Earth's gravity field corresponding with regions of glacial melt and rebound. These aren't just abstract figures, they are tangible markers of Earth's surface changing form. And these changes affect ocean circulation, the movement of tectonic plates, and even the Earth's rotation in minuscule but significant ways. It's a reminder that no movement on Earth, however slow, exists in isolation. Everything is connected: land, sea, air, and even time itself. In seismic terms, the rebound effect is also contributing to stress redistribution along fault lines, particularly in regions that were once glaciated. As the weight of the ice is lifted, the crust begins to expand upward and outward, relieving pressure in some areas while increasing it in others. This alteration in the stress regime has the potential to reactivate dormant faults, triggering seismic activity in places that have not experienced significant earthquakes in thousands of years. These aren't just tremors, they are the Earth's way of adjusting to the new normal. Regions once believed to be tectonically quiet are now under surveillance, as scientists monitor for subtle ground shifts that could indicate a future quake. The implications are profound, especially in areas with aging infrastructure or cities not prepared for such events. But even beyond the technical, physical, and scientific implications, there's something poetic, almost spiritual, about this phenomenon. The idea that the Earth, long pressed down by the weight of ancient ice, is now reclaiming its original shape. It's a slow resurrection of land, a reawakening of forgotten contours, a silent heave of stone and soil reaching skyward once more. It speaks to the resilience of the planet, its memory of form, its quiet patience as it returns, millimeter by millimeter, to balance. For all our machines and measurements, we are simply watching the slow exhale of a planet remembering how to breathe freely again. While glacial rebound continues its ancient work near the Earth's surface, a separate but equally profound process is unfolding deep beneath our feet, far below the crust, where human eyes will never reach. If isostatic rebound is the Earth stretching after a long slumber, then mantle convection is its slow, unceasing heartbeat. And recently, geologists and geophysicists have begun to notice that this hidden force, long thought to move at a glacial pace, may be acting more dynamically than we previously imagined. It's not only shaping mountain ranges and ocean basins over eons, it's also gently, yet steadily, pushing parts of the Earth's surface upward right now in ways that are subtle, complex, and surprisingly relevant to the modern world. It begins with heat. At the core of our planet lies a molten engine of unimaginable energy, radiating heat outward toward the mantle, the semi-solid layer that makes up most of Earth's volume. This mantle, though solid by conventional standards, behaves like an incredibly slow-moving fluid over long timescales. Vast currents of material rise and fall within it, similar to the way hot air rises and cool air sinks in the atmosphere. These mantle plumes, as they're known, can span hundreds of kilometers across and move upward at speeds of a few centimeters per year, a pace that might seem glacial until you consider the immense scale involved. Over centuries, these upwellings of hot rock begin to subtly push the crust upward from below, creating a slow but measurable lift in the Earth's surface. And here's where the story takes a fascinating turn. Scientists are now realizing that some of this mantle-driven uplift isn't confined to ancient volcanic hot spots or tectonic plate boundaries. Instead, it's occurring inland, far from the usual suspects of seismic or volcanic activity. Areas that should be geologically stable, regions not sitting on active faults or near subduction zones, are exhibiting upward movement that can't be explained by glacial rebound alone. The slow breathing of the mantle, it turns out, is flexing the Earth's skin in more places than once thought. And this realization is rewriting what we know about how dynamic the supposedly stable parts of our planet truly are. One particularly compelling example lies beneath the western United States. For decades, GPS data has shown that large swaths of the interior, particularly parts of Utah, Nevada, and even Arizona, are gradually rising. Not dramatically, not alarmingly, but steadily and consistently. This puzzled scientists at first, especially since these areas weren't undergoing significant glacial rebound. But further analysis revealed something remarkable. The rise is likely tied to low density, buoyant mantle material pushing up from below. Essentially, as older, cooler material sinks deeper into the mantle, warmer, lighter rock takes its place, rising like a slow tide of molten buoyancy. It's like the Earth is being gently inflated from within. But why now? Why would this deeply internal process be showing signs of increased activity? The answer, researchers believe, may lie in a broader pattern of mantle reorganization. Over the past few million years, geologically speaking, a blink of an eye, major tectonic changes have taken place. The closure of ancient ocean basins, the shifting of continental plates, and the subduction of massive slabs of oceanic crust have all contributed to changes in mantle flow. And as these flows adjust and redirect, the upward pressure they exert on the crust can shift as well. What we're witnessing today may be the surface manifestation of ancient tectonic history still playing out below, an echo of cataclysms long past that continues to rise, literally, into the present. And it's not just the western United States. Parts of Central Australia, the East African Rift region, and even swathes of eastern Siberia are exhibiting similar patterns of elevation gain linked to mantle dynamics. In these regions, high-resolution satellite gravimetry and geodetic measurements have begun to paint a detailed picture of vertical motion tied to mantle upwelling. While the rates of uplift may be slow, the sheer area affected is immense, raising the possibility that this isn't just a localized curiosity, but a global process still unfolding beneath our feet. As with glacial rebound, the implications are far-reaching. From changes in elevation that affect river flow and erosion patterns to the stress redistribution on the Earth's crust, which, again, can increase the likelihood of seismic activity in unexpected regions, this rising land affects more than just geology. It changes how we understand geography, climate resilience, and even long-term infrastructure planning. A landscape shaped by mantle convection may rise slowly, but that doesn't make it predictable. In fact, the very unpredictability of mantle flow, its fluid chaos cloaked in silence, makes it all the more intriguing and potentially all the more consequential. Moreover, this slow uplift plays into feedback loops with surface processes in unexpected ways. As certain regions rise, their elevation affects local climate. Cooler temperatures at higher altitudes alter vegetation, rainfall patterns, and even human settlement trends. Over millennia, these small vertical changes compound to reshape entire biomes, shifting deserts, forests, and floodplains alike. In a world already grappling with climate instability, the added variable of shifting land elevations, driven not by human action but by the deep breath of the Earth itself, adds a profound layer of complexity to our environmental future. And perhaps the most humbling realization of all is this: for every GPS station quietly recording millimeters of elevation gain, for every satellite peering down to detect gravitational anomalies, there remains far more that we cannot yet see. The mantle, with its colossal currents and mysterious upwellings, operates on a timescale and in a dimension that stretches far beyond the human lifespan. We are only just beginning to detect its whispers. What else might it be trying to tell us? What other forces might be moving silently beneath our feet, waiting to be discovered? It starts as a whisper, an almost imperceptible motion beneath our feet, a silent swell that spans continents. But this slow upward push, this mysterious pulse of rising earth, carries with it ripple effects that are anything but quiet. Because when the very foundation of the world shifts, even by mere millimeters, the consequences have a way of cascading. Not instantly, not all at once, but inevitably. This isn't the kind of change that shows up in the news overnight. It's more like the tide slowly turning, with its impact woven into the fabric of our everyday lives long before we realize it's happening. One of the most immediate, if subtle, consequences of this global lift is the distortion of natural water systems. Rivers that have followed the same paths for centuries may begin to change course, ever so slightly at first, redirecting their flow due to new gradients introduced by the rising terrain. A few centimeters of elevation may not seem like much, but for a river system that stretches hundreds of miles, that tiny difference can influence erosion, sediment buildup, and even flood zones. Communities downstream might begin to notice more frequent floods, unexpected dry seasons, or lakes that slowly shrink as water is rerouted to newly higher terrain. Take the Mississippi River, for example. It winds through the heart of North America, draining vast stretches of the continent. A shift in ground elevation in the upper basin, driven by either glacial rebound or deep mantle dynamics, could have downstream consequences that ripple all the way to the Gulf of Mexico. Floodplains could become flood zones. Croplands that have depended on predictable cycles for generations might be forced to adapt to a landscape that no longer behaves the same. Engineers build for stability, for reliability. But the ground itself is proving less stable than once believed. It's rising, breathing, moving. And then there's the infrastructure. Roads, railways, pipelines, bridges. These were all designed with the assumption of relative geological stability. What happens when that assumption no longer holds? As land lifts, slowly, steadily, it introduces stresses to long, rigid structures. Bridges may begin to tilt. Highways may develop strange warps that weren't there before. In areas where the ground rises unevenly, structures could be pulled ever so slightly apart at the seams. It's a new kind of geological tension, not caused by earthquakes or landslides, but by a slow, upward push from below. And unlike dramatic seismic events, this uplift doesn't announce itself with a roar. It creeps. And that's precisely what makes it dangerous. Because it happens too slowly to panic us, but just fast enough to destabilize the systems we rely on. Think of underground pipelines, oil, gas, water, all carefully calibrated to their surroundings. A small change in pressure due to shifting ground can weaken joints and stress welds. Maintenance becomes more frequent. Failures become more likely. Entire networks may have to be reevaluated as the very bedrock they were built on begins to shift beneath them. But the implications go far beyond infrastructure and industry. As strange as it may sound, there's a psychological dimension to this pulse too, a subtle effect on how we experience and interact with the natural world. Imagine communities in highland regions watching their elevation climb slowly over generations. At first, it's anecdotal. The old well seems shallower than it used to be, or snow stays on the ground a little longer now. But eventually, those changes are recorded in long-term climate data: cooler temperatures, altered growing seasons, changes in how animals migrate, or where certain plants will take root. Farmers in mountainous regions might find crops failing, not due to drought or blight, but simply because the elevation they live at is no longer suitable for what they've always grown. Alpine zones expand, pushing tree lines upward, changing the ecology in ways that are difficult to reverse. New species move in. Old ones vanish. It's like the climate is shifting from the ground up, literally. Meanwhile, at sea level, the opposite happens. In some coastal regions, the land is rising fast enough to counteract relative sea level rise. For now, that might seem like a blessing. Tides retreat slightly. flooding decreases. But there's a catch. As the land rises, it can also strain existing groundwater systems. Aquifers that once thrived beneath certain coastal cities may find themselves pinched or repositioned, affecting everything from drinking water to agriculture. And beyond the science, there's the subtle tension that comes from realizing the Earth isn't as still as we thought. There's something deeply unsettling about that, about the idea that even the ground beneath our feet is changing, quietly, persistently, without our input or control. It challenges the way we think about permanence, about home, about place. If elevation isn't fixed, then maps must change. If landmarks are moving, even imperceptibly, then the concept of stability begins to erode. And with that erosion comes a kind of existential unease, a growing awareness that the world we've built, the systems we trust, are not quite as anchored as they once seemed. But it's not all threat. In some ways, this mysterious uplift could bring new opportunities, fresh landscapes revealed, new resources uncovered, even geologically stable regions becoming more suitable for certain types of development or agriculture as the climate shifts with the land. Perhaps mineral deposits long buried begin to emerge in subtle ways. Perhaps regions long dismissed as flood-prone or unstable are gradually lifted into viability. It's a strange trade-off, old risks giving way to new possibilities. But that, too, is part of the Earth's slow, deliberate dance. And yet, the true magnitude of this shift may not be felt for generations. For now we watch. We measure. We speculate. And we wonder just how far this mysterious upward pulse will go, and what secrets it might unearth along the way. Now, let's consider the atmosphere, and not in the way we usually do with storms or weather forecasts. Imagine this subtle ground swell shifting not just land and rivers, but also the very balance of atmospheric flow. See, Earth's surface isn't just a passive floor, it's an interactive platform that defines how the air above it behaves. When land rises, even slightly, it changes the altitude gradients that influence wind patterns, air pressure, and even the formation of cloud systems. If enough landmass in a key region lifts, even by just a few feet over a decade, it can affect how air circulates across entire hemispheres. Picture a slowly rising plateau in Central Asia subtly redirecting the jet stream. A shift like that, while nearly invisible to the eye, could result in longer droughts in some regions and more aggressive storm systems in others. Not because the weather is inherently changing, but because the ground that governs the wind has risen just enough to tilt the scales. What once was a safe agricultural zone could become prone to flash flooding. What used to be temperate might begin experiencing desertification. All because the terrain rose, the winds adjusted, and now the rainfall doesn't fall where it used to. And then there's the magnetosphere, Earth's invisible shield, the massive magnetic field generated by the molten core deep below. We often think of it as a stable force, always there, protecting us from solar radiation. But in truth, it's an active system, reacting, adapting, fluctuating. And when the landmass above shifts, so too does the distribution of mass within the crust, and that has the potential to alter the way Earth's magnetic field flows through the surface. This is more than just a curiosity. If the Earth's magnetic field starts to wobble even slightly in response to shifting land masses, we might begin to see ripple effects in unexpected areas, like satellite reliability, long-range communication, and even animal navigation. Birds and sea creatures have long relied on the Earth's magnetic signature to guide their migrations. If that signature begins to skew due to slow but steady elevation changes in key geological zones, we could see confusion in migratory patterns. Whales beaching themselves, birds flying in strange directions, turtles hatching only to head towards cities instead of the sea. It's not just tragic, it's destabilizing. Ecosystems are delicate, and when they begin to fray at the edges, the consequences can fan out fast. Think about pollination. If migratory birds and insects no longer arrive at the right time because they've misread the signals of the Earth, entire crops could begin to fail. Regions that have depended on natural pollinators for generations might see sudden declines in productivity. Farmers would scramble to adjust, but nature doesn't wait. The rhythm is off. The dance is disrupted, All because somewhere, deep beneath the soil, the land rose a little more than expected. And what about tectonic pressure redistribution? That's the kind of term that makes most people's eyes glaze over, but the implications are massive. The Earth's crust is a living, breathing shell of interconnected plates, floating atop a sea of molten rock. Every rise in elevation, even if it's slow, represents a release or accumulation of pressure somewhere else. As one area swells upward, it can send subtle shockwaves through the rest of the plate, creating new points of stress and strain. These don't always result in immediate earthquakes, but they do lead to changes in fault line behavior. Faults that were once quiet may become more active. Zones that were considered stable might begin experiencing microseismic activity that builds towards something greater. And all of this, every subtle chain reaction, feeds into human decision-making on a scale most people never consider. Insurance agencies begin noticing strange upticks in structural damage claims. Governments reevaluate risk zones. Urban planners start scratching their heads over elevation maps that no longer align with previous flood models. Engineers are asked to revisit projects built decades ago. What was once safe now seems vulnerable. All because the Earth, without asking permission, has shifted beneath our feet. There's also the psychological ripple, the strange collective awareness that something is happening, even if we can't quite name it. People report feeling more anxious in certain regions. Sleep patterns seem disrupted in mountainous areas where ground uplift is most pronounced. Some suggest that the low-frequency rumble of the Earth's slow rise can have subtle effects on human circadian rhythms, or even mood. It's not that people can hear the Earth rising, but perhaps, in some strange, primal way, they can feel it. A subconscious discomfort. A sense that something isn't quite right. And let's not forget about economic ripple effects. Entire industries are built on the predictability of terrain: mining, agriculture, construction, transportation. When that predictability erodes, even slowly, it begins to upend forecasts, disrupt supply chains, and alter the viability of massive investments. A mine that was once profitable becomes too expensive to operate due to new safety regulations triggered by uplift stress. A shipping route needs to be recharted because a port is no longer at sea level. A farming region begins to fail and requires government assistance, triggering ripple effects in commodity prices. One seemingly isolated geological trend slowly threads its way through the entire fabric of the economy. As we've ventured through the complex and fascinating layers of this mysterious, earth-shaking phenomenon, this force rising ever so slowly beneath the surface of our planet, it's become abundantly clear that the consequences are far-reaching and profound. At first, the idea of the Earth quietly swelling under our feet may have seemed like something only scientists would notice, tucked away in the realm of obscure geological studies. But as we've uncovered throughout our journey, the ripple effects of this subtle, almost imperceptible event could reshape the very foundation of life as we know it. To begin, let's revisit the first point that started this journey: the mysterious pulse beneath the surface. This pulse, an enigmatic wave of activity originating deep within the Earth's crust, seems to be sending out shockwaves in every direction. What was once thought to be a gradual, even benign process, tectonic shifts over thousands of years, has suddenly become a key player in altering the delicate equilibrium of our world. It's as if the ground itself is making a deliberate move, rising up slowly but steadily, quietly shifting the balance of forces that have governed our planet for millennia. What's so striking about this rise, however, is not just its slow pace, but its far-reaching implications. It's not merely about land elevations or seismic changes. It's about the chain reaction it sets into motion. The rise of the land doesn't only affect the geology. It moves outward into the realm of atmospheric changes, redirecting wind currents, altering the behavior of clouds, and even potentially disrupting weather patterns on a global scale. The Earth's delicate weather systems rely on a balanced flow of air, temperature, and moisture. But with tectonic activity subtly shifting the landscape, entire regions could be thrust into new weather realities. Dry zones could become wetter, while once abundant rainfalls could fade into drought. These slow, invisible shifts may take years to fully materialize, but the potential for environmental instability is clear. Alongside these atmospheric consequences, the rise of land could have a profound impact on our planetary magnetic field. Earth's magnetosphere acts as a protective shield, a silent sentry warding off harmful solar radiation. But this, too, could be affected by the strange rise in elevation. We've seen how the Earth's magnetic field has been known to shift over time, and this slow elevation change could potentially add to that unpredictable behavior. It's not just a theory, it's an unsettling possibility that the magnetic fluctuations could reach a point where they affect global technologies, from GPS systems to satellite communication. Worse still, it could throw off the ability of migratory species to navigate, causing rippling effects to ecosystems across the world. And speaking of ecosystems, the potential changes to wildlife migration could have an equally profound impact. Birds, whales, and countless other creatures rely on Earth's magnetic field to guide them. But if the magnetic forces beneath the surface shift subtly, it could confuse these animals, causing them to go off course, misdirecting their migrations. This kind of disorientation could have cascading effects. Entire food chains could be thrown off balance as animals that once played key roles in pollination, seed dispersal, and other critical ecological processes are no longer able to do so effectively. With all these physical changes to the planet, it's only natural that human life will be affected as well. Take, for instance, the shifts in agriculture. As the ground rises in certain regions, it can throw off centuries-old farming practices. Areas once known for their abundant harvests could find themselves struggling with altered growing seasons, disrupted rainfall patterns, and unexpected temperature shifts. Crops that once thrived in specific conditions may begin to fail, and farmers could be left to scramble for new strategies to adapt. The economic ramifications could be severe. Not only would food production suffer, but entire industries tied to agriculture could be thrown into disarray, creating instability in global food markets. The seismic shifts we've explored don't just affect nature and agriculture, though, they're deeply entwined with human infrastructure. Cities and towns built on certain foundational assumptions could suddenly find themselves in precarious situations. Buildings, bridges, roads, and tunnels that were once thought to be safe might face structural failures due to the subtle but persistent rise in elevation. Imagine the costs of reinforcing these structures, or even worse, abandoning them altogether. Entire industries dedicated to construction and engineering would have to rethink their designs and methods, all while dealing with rising pressure to safeguard public safety. Let's also think about the global economy, which could be deeply impacted by the consequences of this geological rise. Industries reliant on predictability, such as mining, construction, shipping, and even energy production, could see their plans thrown into disarray. As land masses shift, so too would trade routes, affecting everything from shipping costs to the viability of certain ports. Companies invested in certain regions might be forced to reconsider their locations and strategies, leading to a wave of economic uncertainty. The ever-present specter of rising insurance premiums and the potential for bankruptcies across industries would make this a financial crisis with the kind of widespread, unpredictable consequences we can't quite imagine yet. But perhaps the most unsettling ripple effect is the one that doesn't leave physical scars at all: the psychological impact. As we mentioned earlier, something as slow and subtle as a gradual rise in land can instill a sense of unease. Humans are creatures of habit, and when those habits are disturbed, when the ground beneath our feet begins to shift, when the weather becomes less predictable, when our technological systems start to wobble, the stress begins to mount. Anxiety levels rise, people begin to question the stability of their world, and that sense of unease can ripple outward, influencing everything from mental health to societal trust. A world that once felt grounded and certain may slowly transform into one filled with ambiguity and tension. How do we adapt to a world that feels less predictable, less in our control? And then there's the political dimension. As the effects of this mysterious phenomenon become more widespread, governments will be forced to react. The need for global cooperation will be paramount, and yet, historically, such massive shifts often lead to fragmentation rather than unity. Disasters, natural or man-made, tend to bring out both the best and the worst in societies. While some countries might band together in efforts to mitigate the effects, others may resort to inward-looking policies, protecting their resources and their own citizens first. National security becomes more critical, and the resources to address these threats could lead to shifting alliances, or even geopolitical conflict, as nations vie for control over increasingly scarce or vital resources like fresh water, fertile land, and energy. At the heart of all of this, however, lies the realization that we are not as in control of our planet as we might have thought. We've built incredible civilizations, harnessed the power of technology, and shaped the Earth to our will. But beneath it all, the Earth has its own rhythms, its own silent movements, and as we've seen, those movements are powerful and unpredictable. The subtle rise of the land isn't just a geological curiosity. It's a reminder that the world is in constant flux, that change can come in ways we never expected, and that we must remain adaptable and resilient in the face of such forces. As we reflect on everything we've discussed, it becomes clear, this phenomenon isn't just a scientific anomaly, it's a challenge, a call to rethink how we view the Earth, how we interact with it, and how we prepare for the unpredictable. The pulse beneath our feet is a force that, although invisible, has the power to reshape every aspect of our world, from the environment to the economy, from the animal kingdom to human civilization. It's a reminder that the Earth is alive, constantly shifting, and no matter how much we try to predict or control it, it will always find ways to surprise us. In the end, perhaps the most important lesson from all of this is that we must remain aware, adaptable, and vigilant. Because while this mysterious rise beneath our feet may seem like a distant, almost inconsequential event, its far-reaching consequences will shape the future in ways we are only beginning to understand. The Earth is not static, and neither are we. The challenge now is to stay grounded while we ride the waves of change. If you've found this exploration of Earth's mysterious rise as fascinating as we have, don't forget to hit that subscribe button and ring the bell so you never miss out on the latest updates. We're diving deep into the unknown, uncovering the hidden forces shaping our planet, and you won't want to miss what's coming next. Stay curious, stay informed, and join us as we continue to unravel the mysteries of our world. Thanks for watching.